Hey everybody, so you probably gathered from the title of this video that our next chapter is going to be about using exponents and using exponent rules. So I want to talk a little bit about where we get exponents from and why they're so useful for us. And now mathematics is looking at patterns and seeing how those patterns interact with each other and seeing how one type of pattern relates to another type of pattern. So if you think about the most basic concept in math, the most basic thing you can do in math is count. Count integers on your finger, 1, 2, 3, 4. You can count the whole numbers, the whole positive integers, 1, 2, 3, 4, 5, and then so on. You can count up however many that you want. But then we want to look at, okay, then what happens if we want to repeat that counting? Like, let's say I want to start at 2 and say, count up 6 more times. Well, when you do that, if you start at 2 and then you count up 6 more, that would be 3, 4, 5, 6, 7, 8 would be your final number because you counted 1, 2, 3, 4, 5, and then ended on that 6th number. But then we want something a little bit easier because if you say, I want to start at 10 and then I want to count up 90 more times, you don't want to have to go through your fingers 11, 12, 13, 14, a million more, 90 more times. You want to be able to simplify that process. And repeated counting, if I say I want to start at 2 and count up 6 more times, well, then we can just memorize that as 2 plus 6 because we're counting up 6 more times. And that's going to give us 8. So repeated counting is addition. And then if you're counting backwards, it would be subtraction. And then if we take it one step further, if we do repeated addition, so let's say I said, so repeated addition. So let's say I started, now I'm at 8, and I wanted to add 4 3 more times. So I want to do plus 4, plus 4, plus 4, plus. So I've got 3 4s there, right? And I want to repeat that addition in 4. Let's just go super easy, and let's just do 4 plus 4 plus 4. Well, we can add those together. 4 plus 4 gives me 8. 8 plus 4 gives me 12. But again, if we want to keep doing that over and over and over again, we want to simplify that process. And a way of simplifying that is what we're doing is we're adding 4, and there's 3 4s. So that simplifies to 4 times 3. So repeated addition simplifies to multiplication. And now we're going to look at, okay, once we have multiplication, what is it when we have repeated multiplication? So if I have the number 3 and I'm multiplying by itself 5 times, there's 1, 2, 3, 4, 5 3s there, we want a way of simplifying that to make it a little bit easier to look at, something easier to memorize. And that's where exponents come into play. So we have 3 to the 5th power, just means that we're multiplying 3 times itself 5 times. So there's 5 3s there. Now, just like we looked at patterns there, we're going to look at patterns that come up when we are multiplying and when we're using different properties or different rules of exponents. So make sure that you are writing down all of these rules as we are going through them. So the first one that we're going to look at, the first pattern that we're going to look at is called product of powers. And what that means is if I have something along the lines of x to the 4th times x squared, I'm looking at two things, and we've talked about this vocabulary before. I'm looking at the base. The base has to be the same. Base has to be the same. And then they're combined through multiplication. So if I write this whole thing out, if I expand this first one, x to the fourth power, just means it's x times x times x times x. And then this one here, I've got x to the second power, so that's x times x. Now I'm just going to simplify it. How many x's do I have that are being multiplied by itself? I have 1, 2, 3, 4, 5, 6. So this simplifies to be x to the sixth power. Now, we don't want to have to do that every time. Just like when we were looking at that pattern of repeated addition, repeated multiplication, we want a way of simplifying that process. Because if I have x to the 50th power times x to the 250th power, I don't have to count all those x's every time. So is there a way that we could use these exponents to get to that 6? How do we go from 4 and 2 to 6? Well, you should notice that 4 plus 2 equals 6. So instead of all this, we could say it's x to the 4 plus 2 power. So the symbolic way of saying this rule is if we have x to the a times x to the b, that becomes x to the a plus b. So what that means is product of powers says to add the exponents. So product of powers says to add the exponents. So that's our first rule for you. We've got a few more to go. All right, so the next one is called quotient of powers, and it's very, very similar to product of powers. Remember, quotient means division, the answer to a division problem. So this is like if we have x to the 7th power divided by x to the 4th power. I'm going to do that same process. We have the same base. It has to be the same base again. So in this one, I'm going to expand it and then simplify it. So on the top, I've got 1, 2, 3, 4, 5, 6, 7. 7 on the top, and I've got 1, 2, 3, 4 on the bottom. Now, when you are dividing, remember anything divided by itself goes to 1, and then it pretty much just kind of disappears because it's just multiplication and division here. So what I'm going to do is I'm going to start canceling things out. I've got 1 pair that cancels out. I've got 2 pairs that cancel out. 3 and 4 pairs that cancel out, leaving just those 3 x's on the top. So I would have x to the 3rd power as my final answer. Now, just like we did before, we don't want to do this every single time, so we got to figure out how can we simplify that. So if I look at 7, 4, and 3, how do I start with 7 and 4 and move to 3? Well, you should be telling yourself that you do 7 minus 4. So the quotient of powers rule says to keep the base the same and subtract the exponents. So quotient of powers says to subtract the exponents. So if I want to write that symbolically, if I have x to the a over x to the b, that becomes x to the a minus b power. So if you're dividing the same base but different exponents, you're subtracting those exponents to get a simplified result. All right, the next one is called power of a power. Remember, power is just another way of saying exponent. So we've got an exponent on top of another exponent. So that's like saying if we have x to the 4th power raised to the 2nd power. So just like we've been doing before, we're going to expand it and then see if we can simplify it. So the inside of this becomes x times x times x times x. And then this exponent says, okay, I've got this quantity multiplied by itself again. So I'm going to have x times x times x times x. And since everything is multiplied here, I can drop all of my parentheses and just use multiplication. So now all I have to do is count my x's. I've got 1, 2, 3, 4, 5, 6, 7, 8. So this becomes x to the 8th power. So just like we've been doing, see if we can figure out a way to simplify that process. How do I go from 4 and 2 up to 8? You should be thinking multiplication. 4 times 2 equals 8. So this becomes x to the 4 times 2. So power of a power says to multiply the exponents. Multiply the exponents. So keep the base the same and multiply the exponents. So again, we're going to write this symbolically. X to the a power raised to the b power is equal to the x to the a times b power. So when you have an exponent raised to another exponent, all you have to do is keep the same base, multiply those exponents. All right, so when you're doing all of these rules, you might encounter the negative exponent rule, because when you're going through and simplifying, if you have a small number like 2 and you're subtracting by 5, that goes into the negatives, and we don't want to deal with negative exponents. So we're going to talk about how to simplify it when you get a negative exponent. For example, if I have x to the negative 3rd power, so think about what exponent means. If I had x to the positive 3 power, that would mean I'm multiplying by x 3 times. If I have to the negative 3rd power, that means when you see negative, you should think opposite. So what's the opposite of multiplying by x 3 times? Dividing by x 3 times. So what this means is, instead of multiplying by x 3 times, I'm going to divide by x. So I'm going to have x on the bottom 3 times. And my top is going to be 1 as a placeholder up there. Anytime that you have to divide and you need a placeholder, you're going to use a 1, because 1 is kind of your placeholder for multiplication and division. So now I've got 1 over x times x times x. Can I simplify that? Well, sure, the bottom I can simplify to just x to the 3rd power, because that's what this was here. So when you have a negative exponent, you're going to flip it. You're going to make it the reciprocal. Make the reciprocal, and then with a positive exponent. So if it's x to the negative 3, remember that's like saying it's x to the negative 3 over 1. You're going to flip it and make that exponent positive. So symbolically, what that's saying is if I have x to the negative a, that becomes 1 over x to the positive a. So you're flipping it. The other way of writing it is if I start out with, I'm going to put a line here. If I start out with 1 over x to the negative a, same thing. I'm going to flip it. I'm going to make the reciprocal. So this becomes x to the positive a, or x to the positive a over 1. But typically we just write it as x to the positive a because you don't need it over 1 anymore. So that's the negative exponent rule. All right, so this next one is called the zero exponent rule. And just like when you have negative exponents, this comes up when you're working on different things, like if you do the product rule or the quotient rule and you're adding and subtracting. Sometimes you're going to get a negative number. Sometimes you're going to get 0 as an exponent, and that's totally fine. Now, the zero exponent is pretty easy to remember, but it's a little bit harder to remember why it's the case. So with the zero exponent rule, I'm going to use actual numbers. if I say 2 to the first power, well, 2 to the first power, that means I just have 1 2 there. So underneath, I'm going to write 1 2. If I do 2 to the second power, well, then I have 2 2s. If I have 2 to the third power, then I have 3 2s. So then if I take it back a step, if I have 2 to the 0 power, well, how many 2s do I have there? You should say that I have 0 2s there, but I got to have something there. Think back to what I just talked about. When you're using multiplication and division, what's your placeholder? Also think about if I'm going the opposite direction. If I'm going from 2 times 2 times 2 to just 2 times 2, what am I getting rid of? I'm dividing by 2 going this way. So going this direction, I'm dividing by 2. So if I keep that trend up and I divide by 2, what is 2 divided by 2? Well, that's 1. So 2 to the 0 power is equal to 1. Another way that you can think about it is all these terms over here, you're actually also multiplying by 1. Because anything times 1 is going to be itself. So 1 times 2, I have 1 2 there. So it's 2 to the first power. 1 times 2 times 2, that's 2 squared. I still have that placeholder of 1. So if I keep going this direction, 2 to the 0 power, that's just 1, and I'm not multiplying by 2's. And if I have 2 to the negative first power, well, then I'm continuing that trend. I'm dividing by 2. So now I've got 1 divided by 2. Keep going, 2 to the negative second power. I'm going to divide by 2 again. I have 1 divided by 2 times 2 because I'm dividing by another one of those 2's. So the zero exponent rule says anything to the 0 power is 1. So the symbolic way of putting that is x to the 0 power equals 1. And that means anything to the 0 power is 1. So, for example, if I had x times y times z times q to the 5th power, and all of that is to the 0 power, that whole thing, that whole chunk there is going to go to 1. So anything, any symbols, any variables, any numbers, anything to the 0 power is always going to go to 1. All right, this next one is called power of a product, and this might sound similar to one we talked about in the past. One of the first ones that we talked about was product of powers. This one flips it a little bit. It's power of a product. So with product of powers, that means you had 2 different powers being multiplied together. In this one, you have 2 things being multiplied together and then a power on top of that. So for example, if I had 2 times 3 to the, let's say, second power. So what I can do with that, I'm going to expand it. So I'm going to expand this whole chunk is to the second power. So I'm going to say 2 times 3 and then 2 times 3. Since everything is being multiplied, I can drop the parentheses and rearrange things. So what that means is I have 2 2's, I have 2 squared, and I have 2 3's, 3 squared. So really what that's saying is I'm just distributing that power into both of those terms. So I'm distributing an exponent over multiplication. So power of a product says to distribute power, and this is the really important part that a lot of times people forget, is you distribute the power, but you have to distribute it over multiplication, not addition. When you're looking at distributing multiplication, that's over addition. But distributing a power is over multiplication. So my symbolic way of putting that one is if I have a times b to the x power, then that's going to be a to the x times b to the x, where a and b are two totally different numbers. All right, I bet you can probably guess what this last one is going to be about. It's power of a quotient, super similar to power of a product. If I have something along the lines of 5 over 3, and that quantity, that fraction, is being raised to the second power, well, what that's saying is that whole chunk is being raised to the second power, so I have 5 over 3 times 5 over 3. And since I've just got multiplication and division, remember you can switch the order of that. So that becomes just 5 times 5 over 3 times 3, which then you can simplify to 5 squared over 3 squared. So essentially what we're doing is the same thing as power of a product. You're distributing that multiplication over division. So you're distributing power. I think I said multiplication before, but you're distributing power over division. So symbolically what that's saying is if I have a over b to the x power, that would be a to the x over b to the x. So that's our last exponent rule that we're going to go through. Now you're going to have practice on Delta Math using these rules to simplify. So I really hope that you wrote these rules down. You wrote them all down on a sheet of paper so that way you have them to reference them. Just like the volume formulas in the past, it's going to be super important that you have these to go off of so that way you don't have to keep flipping back and forth or trying to remember them. You have these rules written down somewhere where it's going to be useful to you. Other than that, that's all I got for you today. Have a great rest of your day, and I'll see you guys in person on Thursday.